Okay, so today we're talking about sketching trig functions, but I'm going to introduce some new trig functions as well. So this is just a reminder, in my garish colours again, that you've definitely seen this in math methods quite recently. This is the generalisation. So in methods, just remember that for all the work we did in transformations of quadratics, cubics, quartics, hyperbole, absolute value function, square root function, all the other ones, everything came down to this. This is function notation. It's a function of x, but you can do four things to that function of x. Absolute value you can do a little bit more. That changes a little bit, but four things to this function of x. You can either multiply by a value on the outside of the function or multiply by a value on the inside of the function. So you either multiply x before you put it in, or you multiply the whole thing after. Or you can add or subtract a value before you put it in, or you can add or subtract a value at the end. They're your four things that you can do to manipulate or transform a function. And those four things do four very specific things to the function, particularly to the graph and the shape and how it looks. They do those four things for any function. It's always true. So the a, if you multiply on the outside of the function by a number, that's a vertical dilation by that exact factor. If you multiply by 2, it stretches by a factor of 2. If you multiply on the inside of the function, so you substitute 2x in instead of x into the function, that's a horizontal dilation, but it's actually a compression of a half, or a compression by 2. So it's a stretch, but it stretches in. If b is a half, then it drags it out. C is a horizontal translation, and if you've got x minus c, it works the way you'd expect it to work. So x minus 4 moves in a positive direction 4 spots, and D is a vertical translation. Always true. Due to some aspects of symmetry, you don't necessarily need all of those. So for example, quadratics are symmetrical. So what that means is you can actually apply a horizontal dilation, which is the same as a vertical dilation, as long as you apply it before you do any of the translations. So you've got, there's some symmetry aspects there that would mean you don't always need A and B. With exponential functions, you don't need C, because C can be incorporated in A for different reasons. You don't always need all of them, or sometimes two of them will do the same thing, or look like they're doing the same thing, but those four things hold true, and they always hold true. So there's going to be an expectation here that you can sketch trig functions. Now, I certainly showed my methods class the way I would do it, and the way I sketch a trig function is to just draw dotted lines all over the grid by starting with the midline, dotted line, the peak, dotted line, the trough, dotted line, a starting point where, say, a cosine has its first peak, and then I add the period on to get an ending point, and then I can easily just draw one cycle in there. That's the way I think is easiest, but you know what? You speak to anybody and they'll tell you that there's an easier way. You have to decide. And if you toy with these in one of these sessions, like I said, you should be putting aside a session to play with the stuff we learn in class and find the way that's best for you, then you're going to be good. That's what we need to be doing. So this is just a reminder of all that. I'm expecting you to know it. I'm expecting you to know that in a sine or a cosine function, that A is the amplitude, D is the midline, and that A plus D is the peak and D minus A is the trough, unless A is negative, in which case that flips. B is the B value, but 2 pi divided by B is the period. So we've got that relationship between the period, which is how often a cycle happens, or how long a cycle is, and the B value. That's an inverse proportional relationship. And the 2 pi comes from the fact that 2 pi is a radian measure. And C is called the phase shift, but the phase shift is a horizontal translation. And we all know that sine starts at a midline in the upwards direction, and cos starts at a peak. So as long as we know that. Similarly for cosine, and also tangent functions, but tan functions they're actually less complex. So they only have a period of pi, and there's less that's going on. There's no peaks or trough. They go up to infinity. So they're actually a bit easier to draw. But we haven't done a lot of the tan function sketching just yet. So here's my 3 new friends. Oh, look at that. I've even written them as a meeting. They are called the reciprocal functions. If you've not written anything down yet, I would like you to write this down, because this is the new content. This is it. This is the kind of stuff, this won't be covered in methods, it won't be covered in general. You walk out of this room now and walk up to any methods or general student, and you can freak them out by saying you know some stuff about cosec theta, but it's actually not that hard. They are the reciprocal ratios. And they come from this. So they come from this question. You might say, like in year 9, and maybe somebody asked this. Cast your mind back. If you're in, say, Miss B4th class in year 9, and she draws up a right angle triangle, and she says, here's theta in my right angle triangle, and she goes, I'm going to introduce you to trigonometry. In trigonometry, sine theta is equal to opposite over hypotenuse, and cos theta is equal to adjacent over hypotenuse, and tan theta is equal to opposite over adjacent. And at some point somebody might have said, well, that's 3 of the possible options, but what about hypotenuse over opposite? Why can't that have a ratio name? And it actually does. It does. That's cosec theta. Cosec theta is the reciprocal of sine theta. It does completely change SOHCAHTOA. So we're not going to change that. We're not reinventing trig. But there are 3 others. There are 6. You know this from combinatorics. You've got 3 different sides. There are 6 ways we could set this ratio up because there's 3 ways of choosing the numerator, 2 ways of choosing the denominator from what's left, 6 possible things, therefore there's 6 possible ratios. But you know what we do? We've done all the hard yards now. We know a lot about sine and cosine and a fair bit about tan. These things here work pretty much the same. The graphs are slightly different, transformations work the same. There's not a lot more that we actually have to learn about these. So it's a pretty simple concept. Why wouldn't you want to know what the hypotenuse over the adjacent is? At a year 9 level, like at a right angle triangle level, you don't need to know. Like ultimately, if you want to find a missing angle and you know the adjacent hypotenuse, well, you can use cosine. Okay, you could do hypotenuse over adjacent and use sec, but that's why we only teach you as much as you need to know. But later on, these do have some benefits in some engineering contexts, but they do have a lot of benefits in terms of proof, and proof is often the link between something we need to know is true, the proof provides that truth. And so these become important in that aspect. Yeah.
Where is like the bottom of the calculator to find that?
That's a very good question. A very good question. So worst case scenario, if we can't find it, if you want to know what cosec 70 degrees is, you do 1 over sine 70 degrees. Just get sine 70 degrees and do 1 divided by that. But I'm sure they're on here. Option. No. Complex.
Isn't it just inverse of that?
No, it's not sine inverse, because that's when you're undoing the theta that's inside the sine. I don't know. They may not be on there, and I will find out for you. The hyperbolic ratios are on there, but not those ones. Okay, let's do some sketching. Cosec theta. Cosec 2 theta minus pi on 3, 2 sec 3 theta, and cot theta. Oh, sorry?
What did cot theta also equal?
Cot is 1 over tan. Oh, yeah, sine, so cos over sine because tan. Why is it that? Oh, yeah, why is it that? That's my question.
That's what we're asking.
I wrote that question.
But you divide it, so you switch.
So, can you say that again, Connor?
It's usually sine over cos, tan is sine over cos.
Ah, thank you. Okay, the reason is because tan theta, as we've seen, is sine theta over cos theta, and therefore 1 over tan theta is the reciprocal of sine theta over cos theta. Yeah? So that just reciprocates to get this. Good question. Thanks for pointing that out to me, Max. So let's sketch cosec theta by starting with, I'm going to do this. I'm going to go to Desmos. I'm not going to sketch cosec theta. I'm going to sketch 1 over cosec theta. What's 1 over cosec theta?
Isn't it just
Sine theta. Excellent. And then we can use that. Restore pages. No thanks. No. Cosec on these things is often CSC.
nice?
Oh. You've seen it now.
So,
Yep.
damn. Wait, I missed it. So it's like literally the opposite. You see where it comes to a peak? The opposite. No, it's the opposite. It's like
Try this again.
it's like everything that is there is not there.
Oh, yeah.
Okay, so we're going to sketch all these onto this graph. Well, not all of them. We'll sketch the first two on this graph, and then we might sketch the other two separately. Okay. So there's sine theta. What does cosec theta look like? Or can you give me some key points?
1 over cos theta.
1 over sine.
You wrote it as on a
Do you know, I understand it's quite frustrating, but the cosec C goes with the S for sine. It doesn't match.
Hang on, did you just say the C goes with the S?
Well, yeah, because here sec goes with cos, and here cosec goes with sine. So you think if they flipped it, if it was the other way around, it would be a lot easier to memorise, yeah? Anyway, it isn't.
Oh, then it looks scared.
Okay, can we sketch this? Cosec theta, can anybody give me some key points?
It's got weird little thingies. Goes through 1, 1.
Goes through 1, 1. So it goes through, at this point, sine theta equals 1. Now, it's not actually 1, 1. Sine theta equals 1 at pi on 2. So I haven't changed my scale to radians, sorry about that.
Nice.
Sine theta equals 1 at pi on 2. And so 1 over 1 is 1. And that's actually true of each of these. And also the troughs. Like that as well. Because 1 over negative 1 is negative 1. So you get the same height. What happens beyond that? I showed you a glimpse of the graph. What does it look like?
Up,
Up. Why?
because it's Gonski. It's asymptotes.
What's the range in between those 2 points? Like,
This is, what do you mean? This is 1 and this is negative 1.
yeah, does it like never go anywhere, doesn't it?
Because of cosec is the inverse of sine.
So cosec is 1 over sine. That means if this is a half, that's pi on 6. Sine of pi on 6 is a half. What's 1 over a half?
1 over half is 2.
2. So there's a mark there. Here's a half as well. So that's 2 as well. So cosec goes like this.
Yeah, but
Like a mini parabola.
And it goes like this. I've got this wrong. Let me get this right. There.
Yeah, because half of one is a half.
And it goes like this.
If you divide it by
You see what's happening here?
actually,
Okay. But what happens along this line here?
It's an asymptote.
That's an asymptote. And what's the value of that line?
Pi. Negative pi.
That's negative pi there. Good. And over here, this line here is, so it's there. That's at pi, and that's also an asymptote. And why is it an asymptote?
Because it can't be the same thing again.
It will
Because it
overlap.
completely flips.
Yep, but why mathematically? So obviously you're giving me descriptions graphically why it's
It's 0.
asymptote.
It's the
It's
line
0 and
that
that's
line crosses.
undefined.
So 0 is undefined?
No, wait, what?
Yeah, it's
In division.
divided by 0.
Okay, good. Thank you. So sine of pi, you were right, but you just weren't enunciating it really as well as I'd hoped. Sine of pi is 0. 1 over 0 is undefined. Okay? So that's why this point doesn't exist. And it goes from negative or from positive infinity to negative infinity because this goes from positive to negative. It's a really small positive number, goes to a really small negative number. So it flips from being 1 over a really small positive number, which is massive, to 1 over a really small negative number, which is massive but negative. So you've got that flip. So that's what it looks like, and it continues on forever like that. That's purple. Now what about cosec 2 theta minus pi on 3? In green, because purple and green go well together. So what is it? It's 3. No, 2. What does a 2 do?
It's
Okay, good. So the 2 is a horizontal dilation, but it's a compression factor inside, so it actually halves the period. So it's going to do that. It's going to compress towards the y-axis. What does the negative pi on 3 do? Shifts it. It's a phase shift. So it's going to shift it out to this new, it's basically this new axis here. Pi on 3 is there. Oh, actually it's not. It's going to be positive though because it's x minus c. So it's going to shift it to here. That is pi on 3. And it's also going to compress it. So you'll see this purple one flips down and back up in between 0 and, I've not done my scale very well, but there, that's where it's equal to 0. Oh yeah, because pi is 3.14, so it's that's 6 and a bit boxes. Now it's going to do it in 3.14 boxes. So it will go there, and it will come up to there, and then that's the first asymptote at pi on 3 plus pi, which is 4 pi on 3, and then it will come down and be negative, but from that 1 mark there, so it will sort of do that, and do it again. So it's done that compression. The green ones are compressed by a half of the purple ones, and a phase shift this way. But again, that transformation stuff is really important. And just to reiterate, your methods and specialists, if you get a transformation question, there's plenty of ways you can go about it. And one of those ways is to not muck around too much with the transformations, but to build up an understanding of the x and y intercepts and the asymptotes and build your graph from that. But you might always get a transformation question that asks you to describe the transformations. So you might have to have a look at a graph and describe how it's gone from the basic graph. Max?
What does an amplitude do in the sec graph?
Here.
Yeah.
Make it further apart from the midline.
Oh, well, yeah, it's a really good question, which has a really interesting answer, I think. We'll play with it in a second. But the amplitude is a stretch. So if you change the amplitude from 1 to 2, it stretches out. So technically, this green thing should move to there.
Yes.
Although because it's reciprocal, it might also move it to there.
What?
Oh, actually,
No,
no. It'll move it out like this. It'll do that. But let me show you on here. No, let me show you on here. It's a good question. This is where I was getting at, because if the sine graph was stretched out, then when you did 1 over 2, which is the new peak, that would go down to a half. So your sec graph would go down. But that would mean that cosec, so your cosec graph, would be equal to 1 over 2 sine theta. So if you change the amplitude of your sine graph, then it's going to stretch the sine graph up, which is going to compress your cosec graph in because of the reciprocal factor. But that's all right, because you're going to get a half cosec theta. So you actually that's going to be a half. So that'll be a compression factor. So that'll work. Let's have a play with it. I see that might not be quite syncing, but let's have a play with it on here. There's my sine graph. Y equals cosec. So cosec is CSC. X looks like that. Now, if we play with, I'll get another cosec x up. I might change this to be y equals A sine x. Add a slider for A.
Press the play button, sir.
Y, I will in a second, but just give me a moment. 1 over A cosec x. And now if I play that, yeah, you'll see what's happening now.
That's getting fat.
Okay, so that's monster's teeth. What do you reckon?
Why is it 1 over 8? Why isn't it just 8?
Yeah.
Yeah, but
Well, because A wouldn't actually be the same. So if I'm comparing A sine x, then the reciprocal of that is 1 over A sine x, which is 1 over A cosec x. So that's your comparison. And if I turn that one off and turn this one off, there's cosec x. If I do 2 times cosec x, it doubles it. If I do cosec 2x, it does that compression that we expected. And if I do cosec 2x minus pi on 3, it's done that compression and slid it along. So there we go. Any questions? Good question so far.
When will we ever use that,
That's also a good question. Hopefully you'll see, when I first started sketching trig functions, I had students say, when will we ever use this? And then we go ahead and use it with tidal motion, moon motion first, like heaps of stuff. There are not nearly as many contexts, but for example, I'm gonna go there. Let's get that, yeah, and let's get this. Y equals 1 over A cosec, and then x minus, what's the? And now you've got teeth. So if you're a graphic designer trying to make teeth, you could do it mathematically. No, I don't. There's tans. You know, we talk a lot about sine and cos. We don't talk a lot about tan. Tan doesn't have many contexts where it helps, and it has no context I can really explain to you. In fact, I don't know any context. And cosec and sec are kind of the same, but they're really handy in proof. And there are engineering contexts where they're used, but I'm not going to probably be able to go there very confidently. But I could do a bit of research. 2 sec 3 theta. I'm going to pause this video and I'm going to get you to sketch 2 sec 3